hey, how are you? Great to hear. Yeah, come in. Make yourself comfortable. Like a drink? Sure. There you go. Welcome to the Tech Lounge. Shall we begin? Welcome to another Chinchilla Squeaks with me, Chris Chinchilla. Today is the turn of an interview from back in, I think it might have been June or July or something crazy like that. Maybe even August. I don't know. Some point in the summer. It's from a small event here in Berlin called Tech Open Air. A little bit of background noise. I've cleaned it up as much as I could. And it is with Joe Fitzsimmons from Horizon, who are in the quantum computing space, but attempting to make the transition for traditional developers into quantum computer programming simpler. So, enjoy. Before we begin, there's just a few people at the door who've got some things they want to tell you. Then we can get stuck in. If you'd rather not hear these interruptions, then please support the show. You can find details in the episode and show notes. Now, I don't really want to dig too much into what is quantum computing, because as you sort of covered in your talk, it has actually been around for a little while. And I think at least listeners to the show are relatively familiar with it. Pretty sure I've had people talking about it before. I'd actually more interested in firstly knowing exactly what is Horizon doing in that space. Let's start with that.
Sure. So if you think about what is necessary to get to useful quantum computing, and we're not there yet.
Yeah.
So, it's an important thing to understand about the field that the systems that exist, the algorithms that exist, they don't outperform conventional computers yet. But to get to useful quantum computing, there's really two things you need. You need to be able to build the hardware to support the computation, but then you need to be able to construct the computation itself. So you need to be able to figure out how are we going to take advantage of interference between different branches of our computation to accelerate the calculation of a quantity we care about. Mm-hmm. And that's really non-trivial. So you said don't explain what quantum computing is.
No, we don't need to, but yeah. Feel free to. Yes.
One part of it, the really important thing to understand is that if you are not taking advantage of interference between different branches of a computation, there is no advantage. It's not computing things in parallel, it's working through interference. And if you can't harness those quantum interferences to gain an advantage, then you're not really anywhere. You could do this on a conventional computer. So if you start thinking about how do I structure a problem in order to take advantage of it, it quickly becomes obvious that we don't have a good intuition for it. It's not how we gain our intuition of how the world works when we grow up. So the way we think about performing computation, we think about how we would do it on pen and paper, for example, and we try to formalize that into a computer program. But at no point do we say, well, I will put myself into a superposition and try these two different things in superposition, and then I'd cancel out that branch through negative interference or something. That doesn't happen, right? That's not our experience of the world. So instead, we struggle with it. Fortunately, enough physicists and computer scientists and mathematicians have been struggling with it for long enough now that we have some basic tools. We have techniques like the quantum Fourier transform, like amplitude amplification and phase estimation, that we can use as building blocks to construct algorithms to start accelerating things like matrix calculations. And if we have those tools, then what we can start thinking about is, can we apply them in a systematic way to go from the user's intent to an accelerated program running on our quantum computer, one that's really taking advantage of these quantum effects to get the processing done more efficiently. So at Horizon, we've been focused on that problem. How do we go from the user intent to an implementation of an algorithm running on hardware? And the long-term approach we've taken to this is to try to tackle conventional code written to run on a conventional computer, and automatically refactor that and try to construct a quantum algorithm from that can be run on a quantum computer with acceleration. And this is not the same thing as just coding up an optimization algorithm or something like this for a quantum computer. Instead, we want to be able to accelerate general purpose computation. We want to be able to recognize what the computation is doing and do it more efficiently on the quantum computer. So that's quite a big challenge.
Okay. Yeah.
But if we can get there, it enables us to put our tools in the hands of domain experts in the different fields that stand to benefit from quantum computation and allow them to build quantum accelerated applications, to be able to take advantage of quantum computing to solve some of the really difficult computational problems that face many different fields across engineering, across, well, I guess we're hearing a lot about AI today, but finance, pharma, all sorts of areas.
And that's not something that some of the other big players like Azure or Google Compute are doing, or just competitors?
So at the moment, we're the only ones that have the capability to construct quantum algorithms from conventional code. And of course, we filed patents on this and so on. Yeah. But what, the challenge here is not to build up a library of, quantum programs that solve one particular type of problem, but to get general acceleration for a program that you don't know has a quantum acceleration beforehand. And that's a big technical challenge. At the moment, the dominant approach that has been taken by some of these companies you mentioned and others is to package up algorithms, to take these variational quantum algorithms, for example, make a Python wrapper for them that makes them easy to integrate into a larger program.
Yeah.
But they do one thing, they solve one problem, and you need to map the problem you care about onto that problem that they solve.
Yeah.
And we're going a different approach. We're saying, can we look at the control flow? Can we accelerate the whole thing?
Bearing in mind some of the competitors you have in this space, they're all big, old companies with relatively large pockets. How do you get started into something like this? Why? And how on earth do you fund it?
Yeah, sure. So, there's different ways you can view this. But the way I view it, with quantum computing the way it is at the moment, there's just not very many people that are experienced in quantum computing. Yeah. 2, 3, 4 years experience, sure. But if you say I want people with 10, 15, 20 years experience, that's a much smaller pool. Mm-hmm. So before founding Horizon, I was a professor, like pretty much all of the others that have started quantum computing companies. Well, not quite everyone, but many have come from that kind of background. Yeah. And if you look at the teams in the big companies, they came from the same background.
Okay.
Many of us know each other and have done for a long time. So it's not really a case of how do we expect to compete with the 10,000 people Microsoft control at something. It's can we compete with their quantum team?
Yeah.
And their quantum team is not that dissimilar from us in terms of background. Yeah. The other side of this is also that there are too many problems and not enough good teams.
Yeah.
So actually, you don't really need to go head-to-head with everyone. There is a potential that quantum computing is computing all over again. Yeah. And if it is, there are so many problems to be solved to get to a quantum equivalent of the world we see today.
Yeah.
There's nowhere near enough people to do it. So we don't need to view this as direct competition between the quantum teams. Rather, the competition is really classical computing, conventional computing. We win when quantum computing becomes the dominant paradigm, not when it is something that's just used for proof of concept demonstrations.
But just on that, no one's ever really going to have a quantum desktop, are they? It's usually going to be behind the scenes.
Not in 2 years.
No. Probably not in a while, but yeah.
I mean, it depends on the technology.
Yeah.
But what I would say is we're actually at this really important point in quantum computing in its development. So for a long time, most of the history of quantum computing has been about making better qubits. And so from 97, 98 until the late 2010s, it has been about making better qubits, being able to do operations with lower error. But at a certain point, we know that incremental improvement in error isn't enough. We need to actively error correct. And to do that, we need to go to larger scale systems. And so, since a number of the hardware companies started working on this around 2016, the investment in the space, both in MNCs and in startups, has increased pretty strongly. And that has brought us from a regime where the number of qubits in systems was doubling once every 5 years to a regime where it's doubling once every 8 to 9 months.
Okay.
So there's a lot of progress happening there. And even at the moment, as some of the shine goes away from some of the variational algorithms where people had hoped there would be an early advantage for quantum computing, but there doesn't appear to be, even as the shine comes off that, the technical progress on hardware means that we're already entering this regime of implementing error correction, of getting to the low noise regime of quantum computing where we're not dominated by errors. And that's the regime where we know there are real applications where there's a real advantage to be had.
I'd like to dig into that a little bit because you've mentioned that quite a few times and in your talk as well.
Sure.
About errors. Like, what in the quantum realm, what do you mean by error? Because I mean, in more traditional computing, it is usually about programming error, but this is sort of something else, isn't it?
Yeah. So this is like a bit flip error.
Yeah.
So, you store some data on your hard disk or on your SSD or whatever it happens to be. There is some minuscule chance that a 0 flips into a 1 without you doing anything, or while it's being processed in the system. But that chance is incredibly small, 1 in a billion billions, something like that. But that's not true in quantum computers. It's like 1 in 100.
Oh, really? Wow.
Yeah. Okay. So we need to push that right out. We'd like to be in the regime of 1 in a million or better, which we may not be that far away from if we can get error correction working.
Yeah. How does a machine, a device, or whatever, know it's an error?
How does it know it's an error?
How does whatever needs to know it's an error?
Well, you don't know unless you put in place some mechanism to check. And usually the way you do this is by, instead of encoding your qubit just as a single state of one system, one physical qubit on your processor, instead you spread that information out over a larger number of qubits in a kind of redundant way. Okay. So if I wanted to do this with conventional computing, one way I might do it is for every bit, instead of having 0 or 1, I might write down 000 or 111. And then if I ever see 010, I know there's a problem. Yeah. But I know also that it's more likely to be that it should be 000 than that it should be 111.
Yeah. Okay.
So I can do error correction in that kind of way. Yeah. But there's more sophisticated ways. So people don't really do this redundant encoding on conventional computers most of the time now. Instead, what you might have is like some kind of checksum. So you say, well, I have these different bits in my program or in my data, and I'm also going to store the sum of them. If I add them up, what's the result? So now I have this check bit that I can compare against, so I can detect if an error occurs.
Okay, and that's all also on the same quantum machine, or that's usually separate? Yeah. Okay. So it's an overhead as well.
Yeah. There was a really nice demonstration of this in December, which I think took a lot of people by surprise.
Okay. I think this sounds familiar.
Yeah. So there's a neutral atom group in Harvard that they do more than just neutral atoms, but they have built this neutral atom setup where they're trapping atoms and using those to store information, and they were able to encode not just 1 or 2 qubits, but they encoded up to 48 qubits in this kind of error detection way. Yeah. And it doesn't satisfy every single thing you would want in a fault-tolerant quantum computer, repeatedly correcting all the errors one after another. But for a single shot, allowing errors to occur and then correcting them, or detecting that the error has occurred, we're at the point of demonstrating that and getting a big improvement already, or at least a noticeable improvement.
And bearing in mind some of the sort of specific use cases that are destined or are currently for quantum computing, we see conventional computing. We often we use these terms of Moore's law and thing, but I think I don't want to say it doesn't apply anymore. It's sort of changed, and now there's a great race. Oh God, I just realized I'm going to say there's an ARM race, because it's mostly not the older kind of Intel structure. It's a lot of the ARM processors are suddenly also jumping in speeds and abilities in certain use cases. Yeah. So, will there still be a need for quantum computing, or will those conventional
alternative architectures catch up to a point where they can handle the kind of problems that quantum was going to handle anyway?
So there's two answers to this.
Yeah, probably it depends.
No, it's not. It's never it depends. So there's two ways you can view this. One is what you're saying really true about the trajectory of conventional computing?
Hard to say. Yeah.
And if you look, okay, clock frequencies leveled out 15 years ago. The rate of growth of single core performance is much, much slower than it was 15 years ago, 12 years ago.
Yeah.
So those aspects of Moore's law have been slowing, but transistor growth is still, transistors are still increasing.
Yeah.
However, there's just not much room left at the bottom.
No.
So we're shrinking transistors smaller and smaller and smaller, but at a certain point you hit atoms and you don't go beneath that.
Yeah.
So are you going to build larger and larger chips? Like, maybe, but again, there's a limit there.
Yeah.
The other thing is that Moore's law, which is what computing has been following for many, many, many years, even if it is now slowing, even if it were to continue, it would lead to exponential growth in our computational capacity, right? So, you know, every 18 months, perhaps, our computational capacity would double. That's not what happens with quantum computing.
Yeah, okay.
So quantum computing, for every qubit you add onto a system, it doubles the hardness of simulating that system. So it's effectively doubling the computational capacity of the system by adding one qubit. So if you double the number of qubits in a system, then you're not doubling the difficulty of solving it. Rather, you're increasing double exponentially the computational capacity of the system. And there is just no way you can run a race against that with something that's increasing only exponentially.
Yeah.
I say only exponentially because people think of this as the stereotypical kind of runaway growth.
Yeah.
But double exponential is like a vertical wall.
Yeah, you showed that in the
So that, you know, that's basically impossible over time to beat. The only thing that's moving is where's the crossover point.
Yeah.
And maybe it gets pushed further out or pulled a little bit closer. But once you pass that crossover point, there's no going back. It's just impossible to catch up.
And when we think of the kind of classic image of quantum computers at the moment, from the last ones I saw anyway, there were these rather steampunky looking kind of brass copper things. And it seems kind of crazy to think that I'd ever own one. But of course, a few decades ago, we could say the same about conventional computers. They filled a room, if you were lucky. And now, I mean, they're tiny. So, you know, when do you think, just ignoring use cases, ignoring if anyone actually needs a quantum computer on a personal level, but when do you think it could be like that I could actually literally walk to a store and just buy one?
Well, you know, there's different approaches you can take to this, but I think for me, the answer is we expect to have our first system running on our premises in February, March 2025.
Okay.
And that's not because we are building the processors. It's not because we're building the fridge. It's not because we're building the control systems. We're going to the manufacturers, buying the QPU, buying the control systems, buying the fridge. And yes, we're building it ourselves. So it's a little bit like, you know, putting together a computer from parts. You know, you buy the processor, you buy the motherboard, you buy the case. So we're essentially doing the integration ourselves, and then integrating that with our software stack. And I think this makes us the first software company in the world, or at least the first software startup in the world, to have our own quantum computer, which is kind of an interesting time, but I don't think we're going to be the last. I think this is the front of the wave, not the end of it.
And how big is that one then?
How big is our the first system? First system's only small. It's 9 qubits. With,
I mean physical size.
Oh, sorry, 2.4 tons. I think it's pretty big. Okay. The physical footprint's about 4 server racks. It's not that large.
Like entire racks?
Yeah, the 19-inch racks you see in data centers.
So it's comparable to maybe the 60s or 70s or something? Maybe?
Well,
80s even?
I can give you a direct point of comparison because we also have one of these NVIDIA DGX H100 systems. And although the system itself isn't that big,
all the coolers and stuff.
Couple of foot high. It's not the coolers. The power density is so high.
Yeah.
We have it hosted in a data center with Equinix, and we have to have it in a rack that is empty, has nothing else in the rack, even though there's plenty of room in the rack. but also the rack beside it needs to be empty as well. So I guess you can see that actually, although the system looks compact, the amount of power that goes through it, you need a bit of space.
Less efficient in some ways because it's just a waste of space.
The power utilization is similar as well. It's not that
really?
different.
That was going to be another question. Okay.
Yeah.
So, there's been this grouping of these, I don't know, they get lumped in with like deep tech or whatever we want to call it, these kind of technologies that are sort of slow burn and they kind of pop up and down in enthusiasm. We're going through an AI enthusiasm phase. But again, most of us know AI is nothing new. It's just a few advancements have, like you showed on your graph, there has been one of those in the AI world. But I got taught AI 20 years ago by professors who were at least 20 years older than me. So it's been around for a while. We had things like blockchain, which has kind of fizzled to a certain extent. And we've had, VR comes in and out of popularity. But again, I think the biggest problem with some of these was there was always, whilst the technology, we could argue whether it had validity or not. It's just people had no real use, is usually what kills something.
Yeah.
And what do you think has kept quantum computing just like ticking along in a relatively small group of people, as you said, with a relatively small user base, and for the foreseeable future, a relatively small potential user base, but it still keeps going and getting funded and progressing seemingly in the right direction, whereas others have sort of fallen by the wayside?
Yeah, what I would say is that it is fundamentally different than many other technologies. Yeah. And I'll tell you what I mean by that. The other aspect is, why hasn't it had a massive boom? Well, it's not useful yet. Yeah. And much and all as people may try to insinuate that it is, or that they're creating value for customers, or however it's phrased, it's not useful yet. Yeah. It's not solving real world problems that people care about. Yeah. So that's, why don't we have the boom yet? But why don't we have the fizzle? It's because if you want substantially better computers, it's the only game in town. Okay. Not a factor of 10 improvement, but actually a different growth curve entirely. If we can get to these systems, it changes what it means to compute. Yeah. It generalizes the notion of computing.
So it's like going from valves to transistors kind of thing.
Well, it's much more dramatic than that, because it's actually changing the underlying model of what it means to compute. The mathematical model of how a computer works changes. Yeah. And when that happens, the rate at which certain applications advance changes very much. So I mentioned a little bit in my talk, if you have certain machine learning models like Gaussian process regression, if you start doubling the number of qubits in the system, you're not doubling the performance of the algorithm. You're not doubling the complexity of the algorithm you can deal with. You're increasing it exponentially. So it's growing double exponentially with time, the size of the model you can handle with your system. And we've never seen anything like that before. Yeah. So if we can get to that point, then it really changes computing at a very fundamental level. And if you go on to like Our World in Data, you can look up the growth of the world economy since the 1800s. And if you plot it on a log scale, it's almost straight line growth, this kind of exponential growth forever, until you get to 1950 or so, which is about the year the first commercial computer is sold. And then there is a kink in that graph, and it grows according to another straight line at twice the rate it was growing before. Yeah. And it continues for the next 70 years.
The whole argument of productivity in computing is a controversial one, but we'll...
Sure, but I agree. And you can attribute a lot of this to like post-World War II growth and stuff like this. Yeah. But if you think about it, if you work back from today, suppose we throw out the computers and we turn off the internet,
it's hard to imagine.
The world collapses, right? Like we cannot have the modern world without computers. We were born in a lifetime
when it was that way.
Yeah.
And I can't remember what I used to do. I don't know. Two final questions.
Sure.
You did say in part of that answer, it's the only alternative. Is that true? Is there really nothing else? No one else is trying any other ideas?
It expands. So what I should... Let me try to be accurate about it. Quantum computing fundamentally expands the model of computation. It encompasses conventional computing, but it expands it further beyond that. There are several sub-universal models of quantum computing, things like annealers and boson samplers, which there's some companies working on, that do potentially give some advantage, but they don't encompass conventional computing.
Okay.
So they become kind of like an add-on for conventional computing. But quantum computing encompasses all of these.
Okay.
They're all subsets of quantum computing. So it's the overarching framework that everything sits inside. And it's pretty hard to beat that. It's the maximal extent within the laws of physics that we know to grow computing. Now, there are some things we don't know. We don't know how relativity reconciles with quantum mechanics.
Yeah.
So it's possible that if we understand quantum gravity at some point, we will understand that there is yet more we can do with computation. And, you know, some people write papers on what you could do if you had a time machine and a computer. But that's imaginary, right? That's not real.
Sure. Well, you said boson, do you mean as in the Higgs boson? Or?
Oh, sorry. Well, yes, but nothing to do with the Higgs boson.
Okay.
So a boson is just a type of particle.
Yeah. Oh, okay.
It has a particular set of statistics. But the Higgs boson is a particular type, one of those type of particles, but it's not the only one.
Yeah.
Usually when I say boson sampling, it's with photons.
Okay.
Photons are also boson.
Okay, cool.
Yeah.
Okay, good. My dad studied maths and physics and would love to probably bring me a primer on many of the things you said. But anyways, let's come back to the last and very practical question. For anybody who's interested in what you're doing, I'm guessing at some point in the future you will be releasing some sort of, it sounds very pedestrian in what we've been talking about, but some sort of SDK or something that people can use in theory? Or,
we've got our own integrated development environment at the moment. We have our own programming languages. We've slowly started bringing users onto them. We did a hackathon late last year with some PhD students. Now we're starting to onboard some partners onto the system. Still closed preview, so just early access at the moment. But we intend to expand the number of people on the system over time. But what's important with us is not, focusing on enterprise engagements and showing like, what does this imply for credit card fraud or something like that? That's not where our interests are. And it's not what's good business for us.
Yeah.
What's good business for us is getting to useful quantum computing as soon as possible. Yeah. And in order to do that, the people we need to partner with are the people building the hardware and the people developing the algorithms that push the boundary of what's possible. Yeah. So that's our focus at the moment.
So that was it. That was our guest today. Thank you very much for joining me in the Tech Lounge. I have been Christian Schiller. If you want to know more about Tech Lounge, head on over to christianschiller.com or please tell your friends about us. It's quiet and cozy in here, but the more listeners, the merrier. You can find more at christianschiller.com/podcast or in the show notes or episode notes, wherever you found this podcast. Thank you very much for joining me, and you're most welcome next time.